All right, so we are the Gulf Coast Hypoxia team. I want to thank all of my collaborators on this project, Storm, Ralf, Gianna, Prem, Alireza, Krishna, and Christian for putting in a lot of hard work this week analyzing some PACE imagery and looking at a non-colored parameter, which was challenging in its own way. So hypoxia is low oxygen conditions below 2 to 3 milligrams per liter in the water column, where it becomes challenging for life to sustain itself. Different environmental factors can induce hypoxia, including nutrient loading, often from rivers draining agricultural land, intense blooms that drive high respiration, and seasonal stratification of the water column that prevents ventilation. This can cause dead zones, which would become an almost yearly phenomenon in the Gulf Coast. So notably for this project, hypoxia and is in ocean color. Hypoxia is not inherently colored, but it can be related to properties that are, including phytoplankton concentration and other environmental and biogeochemical variables. So our project here was to look at how hyperspectral reflectance from PACE can inform our understanding of in situ dissolved oxygen and hypoxia. We looked at the relationships between PACE and bottom water hypoxia in the Gulf Coast, um, mostly based during the 2024 to 2025 PACE data record. And for this project, we focused on the Texas-Louisiana coast and specifically the Mississippi River Plume region, which experiences the most intense and frequent hypoxia in the Northern Gulf. So to address our hypotheses, we gathered a variety of in situ bottom water dissolved oxygen cruise data from NOAA hypoxia cruises, LSU and University of Southern Mississippi hypoxia cruises, and the CMAP cruises in 2024. We pulled in satellite measurements from Sentinel-3 sea surface temperature, and then PACE level 2 remote sensing reflectance from the apparent optical properties bucket. We did some matchups with 3x3 pixel extraction from the level 2 data within plus or minus 1 day of the station measurements of dissolved oxygen. And we omitted wavelengths shorter than 400 nanometers, and we skipped the 590 to 610 bands due to quality concerns. And so in analyzing our remote sensing reflectance to look at bottom water DO at the same location, we used second derivative analysis, linear regression, and multivariate regression. So our first step was gathering together field data sets from these cruises. Fortunately for this work, there's a wealth of dissolved oxygen data in the Gulf and in many other regions of the coastal ocean. And so we had a large number of stations from 2024 and 2025. But notably, even though hypoxia is frequent in the Gulf, only a small fraction of our samples, less than 5%, had dissolved oxygen that was in the hypoxic range. And so a larger data set or potentially future bootstrapping could improve future analysis of this work to try and better predict hypoxia, which we care a lot about, but don't have a lot of samples for. Another notable relationship from the physical data was that for the in situ dissolved oxygen, hypoxia primarily occurs in waters shallower than 30 meters. So across these data sets, we were really only seeing hypoxic bottom water in shallow regions along the coast. And this was true across both the NOAA data and the LSU USM cruises. And so our first thought was to compare mapped PACE data to the Gulf hypoxia data to try to understand whether there were, from visual inspection, whether there are relationships between the color of the water, the AVW, and the chlorophyll A concentration. So shown here for the 2025 cruises and imagery from 8-day composites centered on the 15th of each month from May to August. We see a progression of high chlorophyll along the coast through these summer months. And this correlates with the areas where dissolved bottom oxygen was the lowest, where we had the most hypoxia. If you squint, you can convince yourself that there are some additional patterns here. The large bay in the center of the PACE imagery is Vermilion Bay in Louisiana. And you can sort of convince yourself that there's lower chlorophyll there in June, preceding the hypoxia time in July, and that you might be able to correlate lower chlorophyll along the edge of Vermilion Bay shown here, with some of the lower hypoxia that you see from the cruises shown here. But we also wanted to try and look at actual spectral analyses to see whether there were spectral features that were associated with bottom water hypoxia. So here we have all of the matchups from the NOAA hypoxia cruises and the LSU USM cruise in 2024. Again, with the locations mapped on the right here. What we see is that there aren't a lot of obvious spectral features for bottom water DO like you would see for chlorophyll or potentially suspended sediment concentration. You have a wide range of different spectral shapes here across a range of dissolved oxygen concentrations. I think the one sort of piece that you can clearly pull out of this visual inspection is that you have this set of high reflectance, likely very turbid waters here, none of which are hypoxic. So if we go down now to splitting out by hypoxic and non-hypoxic waters and by cruises, we can see that there are a variety of shapes for the hypoxic samples at these matchups, but they almost entirely don't include these very turbid samples, which might indicate that the most turbid samples in this coastal region are well mixed. So you're having an injection of river water or resuspension of bottom water that are ventilating the water column. But beyond sort of the generally low reflectance and the lack of these uniformly high, very turbid waters in the hypoxic data set, there aren't clear spectral features of the hypoxic waters that we can pull out from here. So to try and highlight these spectral features further, we did a derivative analysis looking at the second derivative of these remote sensing reflectance matchups, colored by dissolved oxygen here. And again, there are some spectral features here. None of them are entirely obvious that you could use as a proxy to indicate bottom water hypoxia. There are these peaks at about 620 and 575 nanometers that are higher in some of the most oxygenated samples, and a variety of other second derivative peaks in the 450 to 500 range that would be worth further investigation for relationship with bottom water hypoxia, but nothing that we can obviously grab onto as an optical proxy for hypoxia. We also just set out to, beyond a visual inspection of spectra and their relationship with hypoxia, we did some regression. So that is the simplest step. We did single wavelength univariate regression, trying to link individual reflectance wavelengths with bottom water hypoxia. And there are relationships here. So there are statistically significant relationships for wavelengths shorter than about 525 nanometers, but the correlation coefficient is relatively low. So there is data here, there's data in the spectra that indicates bottom water hypoxia for both the oxic and anoxic waters, but the relationships are not that strong. And so trying to move beyond this, we also conducted a multivariate ridge regression, trying to retrieve bottom water dissolved oxygen concentration from the full range of wavelengths of the remote sensing reflectances at the matchups. And again, here you have a relationship that is not nothing, but is not a strong correlation, especially at low dissolved oxygen concentrations. These less than in situ observed oxygen less than 2 or 3, which are the hypoxic areas that we're most interested in. So this could be a problem of data set size or of exactly how we're ingesting the variables. And so requires further study. Another important thing that we pulled out of this ridge regression is the ranges of important wavelengths. So we have some peaks in wavelength importance between about 450 and 500 nanometers, which looks similar to what we found for the important wavelengths for our univariate linear regression and could indicate some optical handholds there that you could try to use to fingerprint hypoxic waters. And so the challenges that we encountered are the ones that you would expect from the outset of this project, that bottom hypoxia from space is challenging because hypoxia is not in itself colored. We explored matchups at given points and times, but I think a clear next step that our group would have liked to do if we'd had more time to work on this project was looking at time lag. So using time series analysis of the PACE data in comparison with dissolved oxygen to see whether there were peaks in chlorophyll concentration or other parameters that happened before before the hypoxia occurred. And this seems like a clear next step that would allow you to look at some of the dynamics of the system without having to do full-on ecosystem modeling or other biological modeling to understand the relationship between surface color and dissolved oxygen. And we're also somewhat limited in data availability just by the time period of the PACE data. So the extent and locations of Gulf hypoxia varies from year to year. We only have 2 summer hypoxic seasons available to look at. And unlike a number of other applications of PACE, the number of field samples actually isn't a limitation here. There are many, many dissolved oxygen measurements spanning a variety of coastlines and going back over years and years. So some of our future directions would be incorporate additional data sets in the Gulf. There are other data available from CMAP and the University of Southern Mississippi for 2025. Again, we could do a time series analysis rewinding with PACE to look at how conditions changed over time and how that was related to hypoxia. And then we could also try to retrieve biogeochemical parameters from PACE and other satellites So there's reasonable predictive power if you use temperature, chlorophyll, turbidity, and salinity, which could be inferred from other parameters, and wind speed, all of which you could get remotely and map across the Gulf. And with that, we just want to say thank you to all the people who supported this Hack Week and to the organizers for doing such an amazing job introducing everyone to PACE data, remote sense data, and for the clear and concise coding tutorials. We really appreciate it.